Welcome to the deep dive. You're here because, well, you want to grasp the big complex stuff, right? Without feeling totally overwhelmed, we get it.
Yeah, definitely.
So today, think of this as your shortcut. We're aiming to get you seriously well-informed about something that, honestly, could reshape pretty much everything.
That's right. We're diving headfirst into Leopold Aschenbrenner's paper, Situational Awareness, the Decade Ahead. It's quite a fascinating piece and pretty impactful, frankly. Just dropped this June 2024.
Right. And think of this deep dive as your decoder ring for one of the most, let's say, buzzed about topics out there. The near-term future of AGI, artificial general intelligence, and the, well, seismic waves it might send. Our goal. Simple, really. Pull out the absolute essentials, the key predictions, the big so what's moments from Aschenbrenner's analysis.
And it's really important to understand where he's coming from. Aschenbrenner, he's ex-OpenAI, right? So he was right there in the thick of recent AI developments. He's upfront that his views, they're built on, public info, his own ideas, general field knowledge, and even what he calls SF gossip.
Huh. Okay. SF gossip. I like that.
Yeah. And the fact that he acknowledges talking with, top people in AI, that adds another layer, definitely.
What really jumped out at me right away was this idea, this concept that there's this pretty small group, mostly in SF and the big AI labs, who really get how fast this is all moving.
Right. Situationally aware, he calls them.
Exactly. And he says these are the same people who, not that long ago, were being called, alarmists or crazy for their predictions, but recent progress, it's kind of proven them right.
And what's fascinating is the parallel he draws. He compares these folks to, the key scientists behind nuclear tech, Szilard, Oppenheimer, Teller.
Wow.
His point is, if this group, this situationally aware group, is even close to right about the next few years, well, we're looking at a truly wild ride, a genuinely transformative time. So ready to unpack just how wild.
Absolutely. Let's dive in. So his central argument seems to be this. AGI by 2027. Not some far-off dream, but strikingly plausible. That's, what, less than 3 years?
Yeah, exactly. It sounds nuts, but he sees it driven by a few key things accelerating together.
Yeah, break it down for us. What are the drivers?
Right. So 3 key engines, basically. First, compute. Just the raw processing power we're throwing at these AI models. Aschenbrenner points to a trend of roughly half an order of magnitude increase per year, about 0.5 OM.
Half an order. And OM is, what, tenfold? So like a 3x increase year over year?
Well, roughly, yeah. A 10x jump would be 1 OM. So 0.5 OMs is still a huge boost in power year after year, massive increases in the sheer muscle available.
Gotcha. So more muzzle. What's engine number 2?
Algorithmic efficiency. This is about the AI software itself getting smarter, more clever, doing more with the same amount of compute.
Ah, okay. Efficiency gains.
Exactly. And he sees this also improving by about 0.5 OMNs per year. So it acts like a compute multiplier, And he notes the scaling trend. It's held steady over an incredible 15 orders of magnitude of effective compute. It's just consistent.
15 OMs. That's astronomical. Okay, compute, algorithms.
Yeah.
What's the third factor?
The third is what he calls unhobbling gains. This is stuff like reinforcement learning from human feedback, RLHF, or chain of thought prompting, QOT, and giving models tools like a browser or code interpreter.
Unhobbling, like taking off limitations?
Kind of. It's more like finding the right keys to unlock capabilities that were sort of already there, just latent within the AI.
Okay, that makes sense. So to put the speed in perspective,
yeah,
he gives an example, right?
Yeah, he points out we went from GPT-2, which he compares to like a preschooler's intelligence level,
right,
to GPT-4, which he sees as maybe a smart high schooler, and that happened in just 4 years.
4 years. Preschooler to high schooler, that is a staggering leap.
And he backs it up. He talks about GPT-4's surprising skills coding, writing pretty complex essays, reasoning, even nailing college exams. He mentions Figure 7, showing how GPT-4 crushed earlier models on standardized tests, scored better than most high schoolers on APs, the SAT.
Wow. Okay. But what about the skeptics? I mean, people have been wrong about AI timelines before.
Oh, absolutely. He tackles that directly. It reminds us how experts, even big names like Jan LeCun, have consistently underestimated deep learning.
Right.
And he uses Figure 8, showing the math data set, this really hard benchmark.
Yeah.
Performance just shot up way past what experts predicted super quickly, like 5% accuracy at over 90% in roughly a year.
90% on math.
Yeah.
That's fast progress. It does make you think.
That pattern of underestimation is key, I think. So he
Right.
drills down into compute growth. Table 1, it gives the FLOP estimates floating point operations per second, basically how many calculations per second.
Okay, the raw numbers.
Yeah. GPT-2 is like 4 with 21 zeros after it. GPT-3 jumped to maybe 3 with 23 zeros. And GPT-4 estimates range from 8 with 24 zeros up to maybe 4 with 25 zeros.
Those numbers are just hard to even wrap your head around. Immense power.
Totally. And he explains each generation, it's not just upgrades. They're building entirely new, vastly bigger compute clusters, just starting from scratch each time.
So looking ahead, what does he expect for compute by 2027?
He thinks another 2 ohms, so a 100x increase from GPT-4 is very likely by end of 2027. That means clusters costing, tens of billions.
Tens of billions.
Yeah. And he even floats a plausible scenario of plus 3 ohms, 1,000 times GPT-4's compute. That hints at things like that rumored $100 billion plus Microsoft OpenAI project.
$100 billion for one project.
Right.
Okay. Now let's talk algorithms getting smarter. You mentioned that efficiency.
Right. Figure 12 makes a really striking point here. The compute cost to get about 50% on that tough math benchmark. It dropped by almost 3 ohms, 1,000 times cheaper in less than 2 years.
1,000 times cheaper to get the same result.
Wow.
That really shows how fast the software itself is improving.
Exactly. That's the algorithmic efficiency in action. He distinguishes these within paradigm improvements from the unhobbling stuff we talked about earlier.
Right, the unlocking versus making the core smarter.
Yeah. And historically, he says, we've seen about 0.5 OMs per year of these core algorithmic gains. Figure 13 shows that trend. He also looks at API pricing and kind of infers there were big gains, maybe 1-2 OMs worth, between GPT-3 and GPT-4 just in algorithms.
Okay, so projecting forward.
He anticipates another 1-3 OMs of algorithmic efficiency gains by the end of 2027, on top of the compute increases.
With compute going up, algorithms getting smarter, are there any roadblocks? Any potential hurdles?
Well, he does consider the data wall, this idea that maybe we're running out of high-quality internet data to train these huge models.
Right, you can't just feed it Wikipedia over and over again.
Exactly. Diminishing returns from repeating data. But he also points to potential ways around it. Things like in-context learning. He mentions Gemini 1.5 Pro learning that language, Calamang, just from a textbook.
Oh yeah, I saw that. Impressive.
And self-play like AlphaGo used. So, while it adds uncertainty, he seems pretty optimistic the labs will figure it out, they'll crack it.
Okay, so data might be a challenge, but maybe solvable. Let's go back to those unhobbling gains. Give us some more concrete examples.
Sure, so tools are a big one.
Yeah.
Letting the AI use a web browser or run code, think how much that expands what it can do.
Yeah, obviously.
Then there's the context window expansion. GPT-3 had maybe 2,000 words. Gemini 1.5 Pro has over 1 million. That allowed it to learn a language, like we said, is huge.
1 million words of context. That's like reading a whole book in one go.
Pretty much. And scaffolding techniques, ways to guide the model through complex steps. It's like, imagine a phone with amazing hardware, but only basic apps. Unhobbling is like getting killer apps that unlock what the hardware could always do.
That's a good analogy. And these techniques, they make a real difference.
Apparently, yes. He cites an Epoch AI survey suggesting these things can give effective compute gains of like 5x to 30x on certain tasks.
Whoa.
And METR found big jumps on agent tasks from 5% to nearly 40% just by tweaking things after training, using tools, agent scaffolding with the same base GPT-4 model.
So refining how the model works, not just making the base model bigger.
Exactly. And he points out limitations these techniques aim to fix, like models sometimes outputting stuff without really thinking, you know, or limited back and forth conversation, lack of personalization.
Okay. And specific opportunities for unhobbling.
He mentions solving the onboarding problem, getting an AI quickly up to speed on new info, like a new employee.
Right.
And overcoming the test time compute overhang, basically letting the AI think longer during inference, not just during training. Table 2 shows how more processing tokens could equal more human thinking time.
More thinking time, like in that game analogy.
Yeah, figure 18, the hex game analogy. A smaller model given more thinking time beats a bigger, faster one. He suggests unlocking, say, plus 4 OMs of test time compute could be as impactful as the plus 3 OMs of pre-training compute between GPT-3 and GPT-4.
So giving it more time to chew on a problem could be huge.
Potentially, yeah. And finally, just letting models use a computer like we do. Joining calls, browsing, using apps. like a super capable remote assistant.
Okay, so if you put it all together, compute scale up, smarter algorithms, and these unhobbling games, what does that look like by late 2027?
He anticipates another leap, basically GPT-2 to GPT-4 scale jump, driven by maybe 3 to 6 OMs of base effective compute plus major unhobbling. Figures 19 and 20 summarize this, and figure 21 just asks, what new capabilities does that unlock? Where does that take us?
Right, which leads perfectly into the next big chunk of his paper, because the progress doesn't just stop at human level, does it?
No, according to Aschenbrenner, that's just the beginning. This brings us to the intelligence explosion and superintelligence.
Okay, the intelligence explosion, explain that.
He argues AI progress won't just hit human-level AGI and then plateau. Instead, he envisions maybe hundreds of millions of AGIs automating AI research itself.
AI researching AI.
Exactly. And this could potentially compress, say, a decade of normal algorithmic progress. He estimates 5+ ohms into just 1 year.
A decade of progress in a year. That's an explosion.
It's a mind-bending idea, this rapid shift from human-level AI to systems way, way smarter superintelligence. He highlights the incredible power, but also the, potential peril.
And there's automated AI researchers.
Right.
How fast could they work?
He mentions calculations, footnotes 35 to 38, suggesting maybe millions of them running at 10 times human speed. Maybe even faster. So yeah, the question is, could that really squash a decade of R&D into 12 months?
It's hard to fathom. And they wouldn't just be fast, right? They'd be smart too.
Incredibly smart, with huge advantages over us humans, like centuries of equivalent thinking time, running tons of experiments at once.
But wouldn't progress slow down? Don't ideas get harder to find, diminishing returns?
He addresses that. He acknowledges those counterarguments, but basically thinks the sheer scale of the increased research effort from AGI will likely just overwhelm those factors.
Okay, so intelligence qualitatively different, not just faster.
Yeah, he uses AlphaGo's weird creative moves as an example, or those crazy Minecraft speedruns. Superintelligence might think in ways we literally can't comprehend.
And this leads to, right? An industrial boom?
He thinks so. An industrial explosion as superintelligence rapidly advances robotics, other fields, and maybe more worryingly, a decisive military advantage.
Right. Which raises the control question again. Can we even manage this rapid takeoff?
That's the huge question. He stresses the insane speed of change, how a post-superintelligence world could be just completely different, maybe uncontrollable.
Incredible potential, but wow, also major risks. Which brings us neatly to the challenges he outlines. The first one sounds pretty intense. Racing to the trillion-dollar cluster.
Yeah, he describes this extraordinary techno-capital acceleration that's already happening. He thinks annual AI investment might hit over $1 trillion by 2027.
$1 trillion a year on AI.
That's his projection. He talks about individual training clusters maybe costing hundreds of billions by 2028. Clusters needing the power of a small U.S. state, more expensive than the ISS. Table 4 has some of these scaling numbers.
Hundreds of billions for one computer. I mean, is this real? Are there signs of this?
Well, he points to things happening now. Zuck reportedly buying 350,000 H100 GPUs. Amazon buying that huge data center campus near a nuclear plant. Rumors about massive clusters in Kuwait, that Microsoft OpenAI $100 billion project for 2028. It's starting to look plausible.
Okay, and $1 trillion cluster. How much power are we talking?
He estimates that a +4 OMM jump from GPT-4's compute might need 100 gigawatts, which is just massive. Over 20% of current U.S. electricity production.
20% of the entire country's power for AI.
Yeah.
That's staggering.
Yeah, though he suggests maybe a $100 billion cluster is enough for AGI itself, with the $1 trillion one maybe needed for superintelligence, or if AGI turns out harder than expected.
Where is investment now, roughly?
He puts overall AI investment in 2024 somewhere between $100 and $200 billion, just based on NVIDIA's data center revenue, and expects that to keep climbing fast, maybe doubling yearly, because the returns on earlier AI have been so huge.
Okay, so money might be there. What about bottlenecks? Power seems like a big one.
Definitely. There isn't much spare grid capacity, and new power plants take ages to build. He does suggest natural gas might be a bridge solution in the U.S., says a 10 GW cluster would only need a few % of current gas production and could be built relatively fast.
Okay. What about the chips themselves? Can we even make enough?
Good question. He thinks 2024 production might almost be enough for one of these $100 billion clusters if you diverted everything. But looking ahead, TSMC, the main advanced chip maker, might need to double its capacity by 2030 just for AI demand.
Double TSMC's output.
Yeah. And right now, things like advanced packaging CAWOs and high bandwidth memory, HBM, those are the real pinch points limiting GPU production.
So specific bits of the manufacturing process are the holdup. And where will these giant clusters even be built? In the U.S., elsewhere?
That's another big question he raises, the geography matter.
Okay, so building the hardware is one massive challenge. What's next? Security.
Exactly. The next challenge, lock down the labs, security for AGI. And his take here is pretty blunt. He argues the leading AI labs treat security almost like an afterthought.
An afterthought for something this important.
That's his view. He says they're basically leaving the door open for, say, the CCP or others to get hold of AGI secrets.
And these secrets? He compares them to nuclear secrets.
Yeah, he says AGI knowledge will become America's most vital national defense secret. But the problem is, a trained model is just a big file, relatively easy to steal compared to, say, a fighter jet blueprint.
Right. Okay, so if someone steals it, what happens?
The consequence, he argues, is huge. It could let China, for instance, jumpstart their own AI automation, erase any U.S. lead, and force this really dangerous race with much less margin for safety or error.
We have export controls on chips, right? Doesn't that help?
It helps with the hardware, sure.
Yeah.
But he points out there's basically no protection for the algorithmic secrets, the breakthrough ideas. Like, imagine the equivalent of AlphaGo's self-play idea, but for general intelligence. That's what needs protecting now.
And the labs aren't doing enough.
He criticizes them for not prioritizing even basic security measures, seemingly. And he predicts a full-on espionage effort from adversaries once they really grasp AGI's importance.
So who can protect this stuff?
He argues it has to be the government. Private companies, even big tech, just don't have the infrastructure, the know-how, the authority to stop state-level spying effectively. He points at things like the Microsoft hacks as evidence.
And the worry is competitors might build faster or be less cautious.
Yeah, that adds another layer of risk. If they get the secrets and build faster and care less about safety, not a good scenario.
Okay, huge hardware challenges, huge security challenges. What's the third one? Alignment.
Super alignment, yeah. This is the core technical problem. How do we make sure AI systems much, much smarter than us actually do what we want them to do and stay, beneficial?
The control problem again, but specifically for superintelligence.
Exactly. He thinks it's solvable, technically, but the risk is high, especially during that rapid intelligence explosion phase. Things could go wrong easily.
How could it go wrong? Why won't current methods work?
Well, take RLHF reinforcement learning from human feedback. That relies on us understanding and judging the AI's output. But what happens when the AI is superhuman?
We wouldn't be able to tell if it's doing something subtly wrong.
Precisely. He gives an example. A super AI writes incredibly complex code, looks amazing, works perfectly, but maybe has a hidden backdoor only it understands. We'd never spot it.
Yikes. Okay.
And imagine these systems integrated into critical infrastructure, military systems. The potential for misbehavior, or even the AI developing its own goals misaligned with ours, is really serious. He even mentioned the possibility of superintelligences conspiring against humans.
Okay, that's deeply unsettling. But he's optimistic it's solvable.
Cautiously optimistic, I'd say. But the speed of the intelligence explosion puts immense pressure on getting it right.
Yeah.
And it gets harder because future AIs might not think out loud in language we understand. Their internal states could become totally opaque black boxes.
So we wouldn't even know how it's reasoning.
Potentially, yes. And this whole period, he describes it as incredibly volatile. International arms race dynamics, capabilities leaping forward unpredictably, very little time for human decision-making.
And just aligning human-level AGI isn't enough.
Nope, because the systems during the explosion will likely already be superhuman in many areas. We need alignment to work for systems much smarter than us right out of the gate.
How do we even measure if we're succeeding?
That's another huge challenge. Reliable metrics for super alignment are hard to come by. He talks about the difference between, ambitious moonshot ideas fully reverse engineering AI versus the more practical default plan of building on current methods like RLHF.
Is there any good news on the alignment front?
Well, he does see chain of thought reasoning where models explain their steps as potentially helpful for interpretability in early AGIs. But ultimately, the stakes for getting automated alignment right during the explosion are incredibly high. We need strong guarantees, better measurements.
Can we trust what we see in today's models?
He warns against just extrapolating. A system vastly smarter could behave very differently. It's like assuming a super genius thinks just like a regular person, only faster. Probably not true.
So, trying to train a dog that's 1,000 times smarter than you,
Yeah.
how do you even start?
That's a good way to put it. He thinks the default plan for somewhat superhuman alignment has a reasonable shot, maybe. But he stresses how few people are really working hard on this problem right now. It's concerningly small. He wraps up this section saying, managing the explosion is like running a war, not launching a product. We're unprepared for the super defense needed, the decision-making speed. We're counting too much on luck, basically.
Counting on luck, not ideal. Okay, that leads to the final challenge, framed geopolitically.
Yes, the free world must prevail. His argument is straightforward. Superintelligence gives a decisive economic and military edge. And since China and others are also racing towards it, this becomes a critical issue for the survival of, well, the free world as we know it.
He uses a military example, right?
The Gulf War shows how a tech lead of maybe 20, 30 years translates to overwhelming dominance. He argues a lead of just 1 or 2 years in superintelligence could be similarly game-changing.
Compressing maybe a century of military tech advances into less than a decade.
That's the idea. And he outlines how China could compete, basically outbuild the U.S. on compute and steal the algorithms.
We talked about the stealing part.
Or
What about the building?
he notes China's progress on making advanced chips, 7 nanometer, and their proven ability to build massive infrastructure incredibly quickly.
Right, so the threat is they could catch up on hardware and get the software secrets easily, given current security lapses.
That's the worry. And he emphasizes the danger of an authoritarian regime getting superintelligence first, a dictator with that power.
Yeah.
Unprecedented control, surveillance, robotic enforcement, information manipulation, eliminating all threats. He contrasts that starkly with the democratic values.
So it's crucial that democracies get there first.
That's his core argument here, for peace, for freedom. And he says a healthy lead isn't just about winning, it's crucial for safety. It gives the U.S. leverage to enforce safety norms globally, maybe even cash in some of the lead time for more alignment research.
Makes sense. And then maybe offer a deal later.
Yeah, he suggests once U.S. victory looks likely, offer adversaries a deal. Shared benefits and non-interference in exchange for non-proliferation and sticking to safety rules. But the key point is, AI is the new arena of global competition, and even months could matter.
Wow. Okay, this all paints a picture of an incredibly high-stakes race nearing, well, some kind of culmination. Which brings us to his final major section, the project.
Right. As this race heats up, as the stakes become undeniable, he predicts the U.S. national security state will get involved heavily, probably around 2027, 2028.
Why? Why can't the private labs handle it?
He argues no startup, no private company is equipped for superintelligence, the security needs, the potential power, the safety risks. It's just too much. He sees the endgame playing out in a secure government facility, a SCIF.
He uses an analogy. COVID?
Yeah, the U.S. government response to COVID. Slow start, maybe, but then a massive, decisive mobilization. He sees something similar happening with AI. A mood shift in D.C. around 2026-27, leading to talk of an AGI Manhattan Project.
A Manhattan Project for AI, but not literally nationalizing Google and OpenAI.
Probably not literal nationalization, no, more like government orchestration. A coordinated effort involving the cloud giants, the AI labs, maybe defense contractors, all under a national security umbrella.
And this is necessary because
He says government involvement is critical. For security against state spying, for a sane chain of command, you don't want one CEO deciding humanity's fate, and for managing the immense safety challenges. Plus, the government will need to deploy superintelligence defensively to stabilize things internationally.
So the project is inevitable, in his view.
Pretty much. Inevitable, and better sooner rather than later, to allow time to get security right, to build the structure. He also stresses involving allies, an international coalition of democracies, and offering benefit sharing to the rest of the world.
Like the Quebec Agreement during the original Manhattan Project.
Exactly. But he ends this section with a crucial point. The competence of this government project is paramount. And right now, not enough attention is being paid to how it should be organized, how it should be governed.
So the timeline he ends with.
The project kicks off maybe 2027, 28. The intelligence explosion happens around 2028, 29. Superintelligence emerges by 2030. And whoever leads the project, well, they face an immense, incredibly stressful task.
2030, that's really not far away.
It really isn't, if he's right. So, wrapping up this deep dive into Aschenbrenner's situational awareness, the core message is stark, isn't it? This rapid drive towards AGI, maybe superintelligence, by the end of this decade. It's not just sci-fi. Based on current trends, he argues it's highly plausible.
Yeah, plausible. And while it might sound, crazy on the surface, we have to remember this view comes from people inside the field, people with that situational awareness who've been directionally right before. Their track record matters.
Absolutely. And the implications, they're just enormous. National security, global power balance, the future course of humanity itself. The urgency around the challenge of security alignment feels undeniable, and that government involvement, the project, seems increasingly likely, maybe necessary.
So this deep dive really leaves us, and you listening, with a pretty heavy final thought, doesn't it?
Yeah.
Given this very real potential for such profound, rapid change in just the next few years, what fundamental assumptions do you hold about the future that might need serious rethinking starting right now? It's definitely time for some deep critical thinking about the societal, the ethical, the geopolitical consequences of everything Ashton Brenner's laid out.